All right, yeah, I'm Brendan McMahan, and I'm going to talk a little bit about machine learning, mobile devices, and privacy. I should say, this is work from a lot of different people at Google, not just me. And Google does a whole bunch of different things to kind of protect user security and privacy, and this is just kind of one set of techniques, and it's still, I would say, more on the research side of things. So I'm going to talk a little bit more about the research that we've been doing and not really say a lot about actual applications at Google at this point. So kind of the goal of the team I work on is imbuing mobile devices with state-of-the-art machine learning systems, and we want to do it in a way, see if we can do it without centralizing kind of that core training data and with privacy by default. Why is this important? Well, I think as everybody here knows, kind of our phones now have access to a wealth of extremely personal information. It's extremely useful information from a machine learning point of view or from a product point of view, because access to all of the kind of sensors and digital interactions and everything that goes on your phone, I mean, you know, your location, it's almost always with you. There's a lot of value in that data, a lot of ways it can be used to make the experience of using the phone a lot smarter and a lot better. But the flip side of that is that data can be very privacy sensitive. So what we'd like to do is kind of have the best of both worlds. I mean, this is similar to in the previous talk. You know, you want to get the value from the data without having to pay a cost in terms of user privacy. What's going on? That works. So I'm going to talk about machine learning, deep learning in particular. So we want to train, you know, not just only simple logistic regressions, but kind of state-of-the-art machine learning models with non-convex loss functions, millions of parameters, and kind of complex internal structures. And since we want to do this in a distributed, in a decentralized way, we have to do this on very large kind of decentralized data sets. And the approach we're going to take here is kind of this federated decentralization, where there's a facilitator. You can think about a trusted aggregator who is kind of integrating these individual updates to produce a model for everybody to share. So I'm going to give just a very quick two-slide introduction to deep learning. Essentially, what we want to do is learn a function from some input to an output. So a function from pixels to, you know, is it the digit 5 or what digit is it? And to do that, we're going to learn, we're going to pick a function out of a parameterized function class. So, you know, all of these matrices in a multi-layer neural network architecture. And we define a loss function that basically says what do good predictions look like. We want, and so that defines kind of an optimization problem. And so we adjust the parameters to minimize that loss function, right? That's the kind of problem we want to solve here. And kind of the standard recipe for doing this, and we'll come back to this later, is stochastic gradient descent. So we pick a random subset of the training data. We kind of compute a descent direction that makes the loss better. And then we take a step in the parameter space in that direction. So the interesting question is, how do we do this in a decentralized and privacy-preserving way? So before I get into that, I want to kind of step back and say, well, what's kind of the kind of cloud-centric machine learning workflow for mobile devices look like as it's typically done? So we start with current model parameters in the cloud. And we have some training data, and so we train that model based on the data that's available in the cloud. And then we've got a bunch of mobile devices, these circles here, that come along, and they want to use that model to make predictions. So, I mean, you can think about something like a Google search, or, you know, you go to YouTube, you get predictions for what movies you want to watch, that kind of thing. So you send a request to the cloud. We use that model in the cloud to, say, come up with recommended YouTube movies. And that prediction gets sent back to the device. And this works really well. And there's actually a really nice positive feedback cycle here, because then that interaction with the service produces training data that we can use to improve it. So we see what YouTube movies actually get watched, and that can be used to improve the prediction model going forward. And for a lot of cases, you know, like YouTube movie recommendations, this cloud-based workflow makes a lot of sense. We can't keep the full inventory of all the available YouTube models on a device, and you're going to have to stream the movie from the cloud anyway. So it makes sense to use this kind of cloud-centric view for that type of problems. So we use that additional interaction data to make the model better. In many cases, though, we can do something a little bit different, a little bit more mobile-centric, and that is we can move those models to device. So instead of keeping the model in the cloud and having this request prediction cycle, we actually distribute the model. So we're basically bringing the model to you rather than bringing your request to the cloud. And that has a bunch of advantages, right? Now the service works offline for one because the model is on device. It can save battery. It can save bandwidth because we download the model, when you're on your home Wi-Fi, and then you can use it wherever you are. It's actually nice for app developers as well because the data is already kind of localized. The model's right there, and it opens up new product opportunities. And this also, there's a privacy advantage here immediately because now instead of those requests having to go to the cloud, none of your data has to leave the device because all of the predictions happen locally. And in some applications, that's quite important. What I want to focus on in this talk, though, is not just making predictions, but actually kind of bringing model training onto mobile phones. And that kind of extends a bunch of these same advantages. We can take these advantages even farther if we move model training onto the device. So that brings us to what we're calling federated learning. So the idea here is we want to, this is really a problem, not a particular algorithm, I should say first. And it's this problem of training a shared global model under the coordination of a central server. But then from a loose federation of participating mobile devices, which each maintain control of their own data. So the data is decentralized, but we want to kind of enable these devices to collaborate to train a shared model. So let's kind of go through the same cartoon and think about what this looks like. Now we're going to assume that the training data, kind of each mobile device has its own little corpus of training data. And we start out with a model in the cloud, but you can think of this as initially being just randomly initialized. Now at any given time, many devices will be offline. And what we're going to do is we're going to select just a sample of maybe 100 of those devices to participate in one round of the training. And we want to be a little bit careful about which devices we select. We don't want to put any additional burden or impact the experience of using the phone. So we're going to look for phones that are, say, connected to a free Wi-Fi network and are plugged in with charged batteries. So think of your phone, dreaming while it sits on your nightstand at night. So we'll select kind of a small number of devices to participate. And then each one of those devices is going to download the current model parameters. And now we're going to run the core training on each device kind of independently on that local cache of training data. And then those devices will each contribute kind of a suggested update back to the global model. And then the role of the server in the cloud here is just to aggregate those updates. So for what problems can we apply this? There's a few criteria that makes an application particularly suited to this approach. One is that kind of training data that you have on device is exactly what you want. It's more relevant than data you already have in the server. Second, that data is either large in volume, there's a lot of it, or it's privacy sensitive. So there's a good reason to prefer leaving it on the mobile devices and not having to centralize it. And then finally, you need to be able to, because you're not going to kind of be showing that data to a human and having them label it in some way directly as part of the training process, the labels need to be naturally inferred from the user interaction on the device. So a couple of examples here that are good for motivation. One is language modeling. So when you type into the keyboard on your mobile device, it will kind of often predict the next word you're going to type, which saves you from typing. Even if you're not using that next word prediction feature, there's a language model that decodes the taps and gestures you make because you're not always perfect about it, and so it needs to kind of figure out what word you actually meant. So learning those kind of language models are a really good example of where federated learning can make a lot of sense. For one thing, the on-device data is more relevant because people use their mobile devices differently than, say, somebody writing Wikipedia articles or even somebody writing Gmail, right? We use a lot more abbreviations. We tend to say different things. So having a language model that's specialized for mobile keyboard usage is really valuable. On the same time, I think it's easy to see that the data you type on your mobile keyboard can kind of be arbitrarily privacy sensitive, right? It includes passwords, URLs, text messages, social media. Pretty much everything you enter on your mobile device, right, comes in through the keyboard. So we really care about the privacy of that data. And here the data is also kind of naturally self-labeled, right? So as you're typing, kind of the next word you type is exactly what you're typing in if we don't predict it, so we learn what the correct prediction is in each case. Federated learning presents a bunch of challenges from an optimization perspective. I'm not actually going to go through these because I want to make sure I get to the privacy part of it, which is the main of the talk, which is the main focus today. But this was really some of the motivation for introducing the phrase federated learning, because it is in some sense a distributed optimization problem to train these models, but the standard assumptions that get made in the majority of the distributed optimization literature just don't apply here. We're kind of on different scales, different assumptions about how the data is distributed across the compute nodes and so on. So before we can talk about privacy, we need to talk about how we can kind of solve this problem without privacy. So I want to introduce the algorithm we've been using for this. It's actually kind of funny. We initially implemented this algorithm expecting it to be kind of a baseline because it was an obvious first thing to try. And it ended up working well enough that we haven't had to spend a lot of time developing more sophisticated algorithms. So this steps through kind of in the procedure I just described. The server is going to select a random subset, say 100 devices, to participate in the training. In parallel, each of those devices downloads the current model parameters. And then locally, essentially each client is going to run stochastic gradient descent over their local data to compute the update. So if we were just going to kind of run stochastic gradient descent, all each client would do would be kind of compute one gradient and send that back to the server. But instead, what we're going to do is take multiple local steps of stochastic gradient descent to hopefully compute kind of a better update. And the reason that's advantageous is that in federated learning, our main kind of constraint is communication bandwidth, right? You have to have a mobile device download the current model, which can be fairly large, think 5 megabytes or something for a moderately sized mobile model, and then upload the resulting update, which is about the same size. So compared to doing that same kind of computation in the data center, we're, I don't know, 3 or 4 orders of magnitude slower in terms of the network. So it's advantageous to do a little bit more local computation, which is relatively cheap once you've downloaded the model, in order to get a better update, and then hopefully have to make fewer iterations of the overall protocol. Yeah?
Have you guys looked at using second order methods at all? I mean, obviously computing the Hessian is unrealistic here.
Right.
But using some kind of second order information to reduce the number of rounds of...
Yeah, I mean, you could do that potentially locally, just in kind of the inner optimization, or globally over all of them. So we've certainly thought about it, but we haven't tried it yet. Like I said, this has been kind of working well enough that it so far hasn't been the bottleneck for us. And then, so once the client has kind of computed these updates, just the change in the model parameters recommended based on the local data, it sends those to the server, and the server's job is really easy. It just kind of computes a data-weighted average of those updates and applies it to the current model. So just to quickly give some experimental results here, this is a large-scale next word prediction problem. And compared to a baseline that's already pretty good, this kind of large batch federated SGD, using this federated averaging approach, we get a 23x decrease in communication costs. So we're able to train a fairly reasonable model in like 35 rounds of this procedure, which is awesome. Similar results for CFAR. This is a standard kind of image classification task that neural networks are very good at. Here, compared to kind of a baseline of like data center style SGD, again, we get like a 50x decrease in the number of rounds of communication we need to get a reasonably accurate model. And more importantly, kind of the number of rounds we need, hundreds to thousands to get a reasonable model. That's the kind of thing that would let you train a good model in the real world in a few days or weeks, even if, or less than a week, even if each round was taking, say, 5 minutes or something like that. It varies, but you know, 1 to 5 megabytes or something. You know, depending on you know, think 1 million parameters, 5 million parameters, and there's tricks you can play with, you know, quantizing those models and compressing the updates in various ways that I'm not that will decrease the actual size. But think a few million parameters as being typical.
So again, just to understand the baseline here, SGD is sort of just one. When you say SGD, it's just like one user sample at a time?
SGD, yeah, is actually you just kind of pretend you had the data in the data center and ignore kind of any user partitioning and just kind of take one step on a mini batch of like 50 examples. Federated SGD is essentially doing kind of a large batch gradient descent where you take all of the data from, say, 100 users. So that would be like essentially like taking an SGD step on a few thousand examples instead of 50. So that actually, just using those larger batches, if you tune the learning rate a little bit, actually helps a fair bit. And then federated averaging adds in, instead of kind of just computing a single gradient on each of those selected users, you actually kind of iteratively take a bunch of gradient descent steps before averaging. So that's optimizing these kind of models is an inherently kind of iterative process to get it right. And so by kind of, we're able to move kind of some of those sequential steps onto a single device. I think that's the best intuition for why this speeds things up. All right, so now we've kind of got the basic story of how we want to train these models. Let's think about this from a privacy perspective. So the place we need to come back to is where the server starts aggregating these updates. This is the first time that any information leaves the client mobile device and goes to a server. And so the obvious question is, you know, do these updates that get sent to the server potentially contain privacy-sensitive data? And the answer is obviously yes, they could. It's less information than if we sent the whole raw data set, right? Substantially less information, just from an information theoretic point of view. But that's not to say that you couldn't infer quite a bit from a user if you inspected one of these individual updates. The details obviously depend heavily on the particular model you're optimizing, kind of how hard or easy that attack would be. I think it can range from totally trivial, like, you know, you see a particular coefficient is non-zero, and that means the user used this particular word or this particular phrase. For other kinds of models, I think it would be quite a bit harder to attack the updates, but I'm sure it's doable. So there definitely can be sensitive information in these updates. But already, before kind of introducing anything new, we already have two pretty important things going for us. One is that these updates are ephemeral. So unlike, you know, when you log kind of training data, if you're going to train models in the cloud, typically you would hold on to that data for some amount of time so you could train different models and use it. Here, we can kind of apply these updates, aggregate these updates and apply them to the model and then discard them immediately. So we never have to store them. And kind of going back to the previous talk, storing private information actually comes with substantial risks, or I should say maybe a substantial responsibility to protect that data. So if we don't need to do that, it's nice to be able to discard those updates as soon as we've used them. Second, and it's already hinted at this is a very focused collection. We're not sending all the raw data. We're trying to send really the minimal thing that is sufficient to improve the current model. So that's again better from a privacy point of view. The next point is that aggregation step that the server had to do was very simple. It was just a simple data-weighted average of the individual updates, and that was by design. So in fact, all the server really needs to know is the average of those updates, or the sum of the updates. It doesn't care about any individual update. So you know, the ideal thing here, well, wouldn't it be great if Google kind of could provably not see the individual updates and only got that aggregate? So this gets into secure multi-party computation, secure aggregation, and we've actually done some work on efficient protocols in this space. One of the key challenges for doing secure aggregation with mobile devices is the limited availability of the devices. The devices can kind of disappear at any time. So you need a protocol that not only handles kind of securely aggregating not a handful of values, but these kind of million-dimensional model parameter vectors, but you also need a protocol that's robust to devices participating, kind of dropping out. You still want to be able to recover. So you want to be able to select, you know, 130 devices, but still complete the protocol if only 100 of them stick around. And then finally, we can actually ask a different question. Say we're already doing secure aggregation. We're not worried about Google seeing the individual updates because they're ephemeral and they're not stored. But we're still kind of training a final model here, and that's going to get sent down to mobile devices. So we might worry that that model might kind of memorize a particular user's data. This gets at kind of some of the recent work on membership attacks and model inversion attacks and so on. And so this is where differential privacy comes into the story. The basic idea is instead of just doing the kind of exact sum of the models, we want to be able to add some noise, right? That's proportional to any one user's update. In order to actually get a differential privacy guarantee, though, we're actually going to need to make a few changes to this federated averaging algorithm. Some of these are really critical, and some of them are more technical to let us prove the appropriate guarantees. The first one is instead of selecting, say, a batch of exactly 100 users, we want to select users independently with a probability Q. So we'll get in expectation, say, 100 users. But now we actually have a variable size set of users on each round. The fact that we're doing the sampling that way is mostly for technical reasons. But because we're adding noise, we're actually going to need to select a much larger number of users per round as well. Because the noise that we need to add is noise proportional to one user's value. And so we can kind of decrease the relative effect of that noise on the average by adding more users. And that turns out to be a critical degree of freedom we have here. The next thing is we need to bound the influence of any one user's data on the final average. And if one user's data could be a billion, there's no way to do that. So we need to apply a clipping step. So we bound the maximum L2 norm of any one user's data. And there's, again, a few different ways you can do that. But the key is that if you view it just as a single parameter vector, you assure that each user is only contributing a model update that has bounded L2 norm. Then because we're doing an average here, we have to be, again, for kind of some technical reasons, a little careful about how exactly we compute that average. We want to do something more like a sum if there's kind of user data, or we're trying to use a private estimate of what's in the denominator, we have to worry about exactly how we compute the sensitivity of that function. So this is another kind of more technical point. And then, of course, the final change, and maybe the most critical one, is we have to add the appropriate amount of Gaussian noise to the final model update. So there's really four big changes to the algorithm we've made here. And the question is, how are these going to influence those convergence properties of the algorithm? The main technical tool we're using to do this is the moments accountant that lets us kind of track our privacy cost in a very efficient manner over multiple rounds or multiple iterations of the protocol. So I'm not going to say too much about the technical details in the talk. The reference is there if you want to look at the details. But this is a key piece of theory that we're building on, and it's what necessitates, say, the random sampling with probability Q for each user. Now, I want to go back to this side where we said, hey, we had this huge decrease in communication costs. That means we only had to run this protocol 23 times fewer. This also has privacy ramifications. From a privacy point of view, this means we only need to query the database, the private database, this decentralized data set, say 35 times instead of 800 times. So there's a really nice synergy here that using an algorithm that's more efficient from a communication point of view actually ends up also being very beneficial from a privacy point of view. One of the challenges then of making this work is we now have some additional hyperparameters we have to worry about. So this is looking at the effect of that clipping parameter. And so we can see if we're too aggressive with the clipping, you can ignore the two different kinds of lines. This is just accuracy after different numbers of rounds of training. That clipping can really slow the convergence of the algorithm. But we can look at this plot and say, hey, if we pick a value of like 20, clipping doesn't really hurt. So far we haven't done any privacy or anything. We're just looking at the impact of that one parameter. Now we can fix, say, clipping at that level and look at the effective noise. We're still kind of using only a small number of users per round, and we're looking at just the absolute amount of noise we're adding. And again, we see if we add too much noise, training kind of completely blows up. Accuracy goes down to basically what an untrained model would get. But if we pick a reasonable amount of noise, like something like a standard deviation of 0.006 in the final average, then it doesn't seem to hurt training too much. So we can put these ideas together, and the key is that those initial experiments get us into a reasonable parameter range. And so by picking something like a standard deviation of noise about 0.003 and a clipping level of, say, 15, we can get a model that's very comparable with a non-private baseline in terms of accuracy. And we can get a pretty good level of differential privacy. So 4.6, an epsilon of 4.6 for the actual data set size. One of the key observations, though, is if we just run this on a bigger data set, an actual kind of internet scale data set, the privacy is a lot better thanks to amplification via sampling. What's different than the baseline is for the baseline we were using only 100 users per round. In order to get the noise level small enough to get down to that 0.003, we would need to use like 5,000 users per round. So here, privacy is not really costing us anything in accuracy. We've got a very comparable model, but it's actually costing us quite a bit in terms of computation because we need to run a few more rounds of training because of the noise, and we have to use 50 times as many users per round. But this is actually kind of nice because computation is getting cheaper, and so being able to kind of pay computation instead of paying accuracy is really much much better from the point of view of being able to deploy this in real systems. And I think I'll pretty much end there. So I should say this was differential privacy in the trusted aggregator setting. We are interested in moving towards more of a local differential privacy guarantee. But that is, in combining kind of differential privacy with secure aggregation and being able to say something about the guarantees that provides. But that's kind of ongoing work. And kind of in conclusion, differential privacy is very complementary to the benefits that federated learning was already providing. So if you want to learn a little bit more, we had a blog post on federated learning back in April that talks a little bit about how we're using this technology in Gboard now, not with differential privacy or secure aggregation yet, but we do have the system deployed in some real products. And there's plenty more work to do. So I'll leave it there. Thanks.
All right, we've got time for a quick question and a minute or two for questions. Yeah, Gillette.
So, when you talk about secure aggregation, I believe there would be some round of interaction between the users.
Yes, that's right. That single communication round, I think our protocol is like 5 kind of rounds inside that. Okay. Yeah, it's a fairly complicated protocol. So there is a pretty substantial cost in terms of at least the complexity of the protocol to implement secure aggregation. That's right.
Sorry, yeah.
And how much of the conclusion that you had about it costing only more computation as opposed to accuracy do you think that's coming just because of the vast amounts of data that
right. The caveat there is for a sufficiently large data set, where large here means large number of users. I should say, I didn't mention this explicitly, one of the advantages of this approach is we're actually getting user level differential privacy, not example level, because we're bounding the contribution of each user. That's kind of the atom of privacy we're working with. But you need a lot of users to make that work. The advantage is at Google we tend to have a lot of users.
I think your number was like 100 million.
I can't remember. Yeah.
Right.
Which is not unreasonable for a lot of. But even for 1 million users, like we can start to get something reasonable. That seems to be where, at least for these models, we could get the noise low enough.
Not every application has.
That's right. That's right. The other thing, though, we kind of made things harder for ourselves by training these models from scratch, training purely from random initialization. For most of these applications, something like language modeling, there's no reason to train from scratch in practice. What you would do in practice is you would train kind of a reasonable language model on public data, and then you would just refine it to work on the particular distribution, to work on mobile usage in particular. And so that should let you use kind of quite a bit, many fewer rounds of communication even than we needed here. Yeah.
One quick quick question. So there's a fair amount of parameter tuning going on here.
That's right.
How transferable is that across domains?
That's a really important question for open work. I think, like right now, getting this to work, right, we had to run quite a few experiments to get the right parameters. And of course, you have to do a fair bit of parameter tuning to get neural network training working in general. I think what we have in this paper up on arXiv now is a reasonable recipe for doing that parameter tuning. What I'd really like to see is more adaptive techniques that would make that parameter tuning unnecessary. We've started doing some work on that, but there's still more to do. Yeah.
So I actually got to read that paper earlier, and I can't remember if you did at all changing the bounds on the gradient, because that's one of the things you're using to ensure privacy, right? The bounds on the
That's right, that's right. Whether we're tuning that parameter adaptively. In most of the initial experiments, we didn't. We ran one experiment where we kind of restarted training and changed it once, and that does seem to help. So either using kind of an appropriately chosen schedule for adjusting those clipping parameters over time seems likely to help. Of course, that means you're now in even a much higher dimensional parameter tuning space. Or maybe even better would be kind of using an adaptive process to kind of measure the actual norms of kind of the unclipped gradients and use that to guide.
Sorry, and also like when you get enough users, probably it's easier to go with a higher gradient budget.
That's right. Yeah, exactly. So the clipping and the noise and the users go together. So if you use more users per round, you can afford to just use a larger clipping parameter. So in some sense, more users and more computation, if you have the users and the computation, solves most of your problems here. And I think that's one of the biggest takeaways. Yeah.
Okay, so let's take the remaining questions to the break. So let's thank Brendan again.